So I think we can start. It's a pleasure today to welcome Crispin Keable from Atos. As most of you know, Atos is our partner in the supercomputing waves project. Crispin today is here not to talk about traditional HPC, but to give us a window on the future of quantum computing, and in particular to describe this exciting Atos project, which is called the Quantum Learning Machine. Crispin has been in the field of computing for over 30 years, I believe. He has seen lots of technology going through, and now he's here to tell us about this revolution and in particular take that Atos is having with it. So I'll leave Crispin to tell us about it.
Thanks, Pietro. Yes, I stopped being an academic about 30 years ago. And 30 years ago, I was an astrophysicist. That's why I did a PhD in computational cosmology, just when computational cosmology was beginning as a thing. And my great hero was Richard Feynman, as he is, for lots of people. Richard Feynman was so interesting, partly obviously because of his quantum electrodynamics, he won a Nobel Prize, blah, 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 but also partly because of his fantastic ability to explain ideas and to do it with humour and to really go where rational thought took him. At the time when I left academia, in the 80s, I knew that Richard Feynman was working on quantum computing. And at the time, I thought, even really smart people like that can get it wrong sometimes. And now here we are 30 years later, and I'm just realising how stupid I am. Because actually, we've got to a point now where quantum computing has moved from being this very kind of esoteric thing to being something which is not quite there. Maybe it's 5-10 years away. But the developments are coming thick and fast, and it's moving out of the lab, I suppose, and into the more mainstream. So what I was going to do today was to talk a little bit about what quantum computing is, just to sort of level set, perhaps, quite basic, and then talk a little bit more about what we do at Atos, why we're doing what we're doing, which is a different approach to quantum computing compared to a lot of people, and then maybe give you. I've actually got on my laptop a little version of the QLM, which is just a sort of software environment that you can play with, and it's part of the QLM. So. Oh, and please ask questions as we go along. So the other thing to say is that as quantum computing comes out of the lab, it's much wider than its applicability is much wider than just for sort of physics type problems. And so, I've got some examples about biomedical computing here. But, first of all, why do you need quantum computing? What's the requirement for quantum computing? And I'm going to try and rearrange this so it's easier to. So, high-performance computing has developed, obviously, over the years, but in relatively recent time, I suppose, in the last 10 years or so, we haven't had the same kind of processor getting faster and faster, the kind of Moore's law performance improvement that we have enjoyed previous to that time. But at the same time, people's desire for the use of high-performance computing has not abated at all. People in a wide range of different disciplines have got more and more data to deal with, to analyse, and with which they can see value. And so, how do you deal with that? Well, the sort of exascale type supercomputing programs are talking about using tens of megawatts to drive the computer, which is kind of like, it's a little bit crazy in a way. There's this increased need for computing, but there's no technology, if you like, that delivers that, and that, in a way, is I suppose one of the drivers behind quantum computing. So, to think about quantum computing, I've got this example of a trial. We know that qubits and bits, that in quantum computing there are these entities called qubits. And a qubit is the quantum analog of a classical bit. But it behaves differently. And it's that difference in behaviour that is really interesting. It's what makes quantum computing more powerful. What is it? So the analog there is a trial. At the beginning of the trial, there's a defendant, and you don't know if the defendant is guilty or innocent. So the probability of guilt or innocence is 50-50 either way. And that's really, how you might think of a qubit. This notion of superposition, could be 0, could be 1, is the analog of the state of the defendant at that point. But then you present evidence to the court, and that evidence actually modifies the guilt or innocence probability, and that's the analog of the quantum program. So at the end of the trial, then you have a much more definite idea about the guilt or innocence of that person. And so that's the sort of the thought that which you can think of to look at qubits. But you might also know that the individual actually didn't do the crime on their own, that there was another person involved. And the consequence of that is that presenting evidence for the purple person actually convicts the green person as well. And so you have this notion of entanglement there. And these two ideas of superposition, which is to say, the qubit can be in any state initially, and entanglement, those are the two ideas that make quantum computing as powerful as it is. Because it gives you an exponential growth in the data content of a machine. And it's that exponential growth which is far, far more powerful than a classical computer. So, just written our first quantum program, if you like, with that. In the same way that in classical computing theory, you can decompose problems into very simple entities like AND and OR gates. There's a universal theory of classical computing. The same is true in quantum computing. You can decompose complex algorithms into much, much simpler entities. So these quantum circuits, as they're called, operate in a very similar way to the way in which a classical computer works. But they're actually operating on the quantum properties of matter. And so you don't have the direct analog of a logical operation. Instead, you're doing quantum mechanical operations on the qubits, or on the quantum entities. And so you have these things which are not familiar to us, like a Hadamard gate. The C NOT gate is a controlled NOT gate, so that is a very familiar thing. But the Hadamard gate is one of the important gates that there are, and it does something effectively quantum in nature, and we can come on to that as we go. But it's really, in terms of learning how to deal with a quantum computer, there is a kind of a transition really to thinking about how to decompose problems into those sorts of entities. The other thing to think about, or to realise, is that quantum computing has tremendous potential power, has tremendous speed-up potential, but not for every problem. And by the way, not the same amount of speed-up, if you like, for all classes of problem. So what I'm trying to show here is the thought that some algorithms will speed up very well, some algorithms will speed up less well, and some algorithms won't speed up at all, in fact. So it's not the panacea for everything. Quantum computing is not the panacea for everything. What this is actually showing is a list of. These are well-known algorithm names in quantum computing, and they can be sped up at different rates depending on the algorithm. So we don't expect quantum computing to be, or we don't expect to have quantum computers that are you just use the quantum computer on its own anytime soon. When quantum computers do become available, we expect them to be more like a speed-up box for a conventional computer. So we see more the thought that like a GPU in a machine today. So you use a GPU for certain classes of algorithms which can be put onto the GPU. Similarly, with a QPU, it'll be an accelerator rather than anything else. So we think of quantum computing more as a sort of hybrid problem. One of the things that you can't do with quantum computing is to branch or to loop. These are obviously the things which we all use to program computers with all the time. Now, you don't need to loop very often because all of the qubits are doing all of the calculations all of the time. So often you can get away without needing to do that. But there are problems where you do need to do those sorts of things, and for that, a hybrid approach is probably the right one. So this foil shows the sorts of algorithm areas where quantum computing might be applied. Those algorithms I showed on the previous slide, Shor's algorithm, very famous algorithm for factorizing numbers, so everybody gets worried that the internet will be broken when quantum computers become a real thing because of Shor's algorithm. But actually, and Grover's algorithm similarly, it's a database search function algorithm. In recent years, people have come up with a range of different application areas, which are represented here across a range of different disciplines. And if you are interested in quantum computing for your own work, then I would recommend going to the Quantum Algorithm Zoo website, where somebody's created a long list of now more than 200, I think, different application areas, or different algorithms for those applications. So it's a point now, quantum computing is at a point now where it's really growing in terms of its applicability to all of these different areas. and some of them will be some of them will be earlier, I suppose, in terms of when they can go on to quantum computers, and some of them will be later. So, for example, Shor's algorithm, as I mentioned, as I was talking about earlier, Shor's algorithm works, has been demonstrated to work theoretically, but won't be able to crack a big RSA key until you have a quantum computer that has thousands of qubits, and by the way, the noise has got to be very, very low indeed. So that probably is not going to happen in the next, 10 years. We do expect things to move quite quickly, but I certainly don't think that it's a big problem from that point of view, that the internet will be broken tomorrow, as it were, as our bank websites get cracked. So the state of quantum computing today, we are at a point where the top left really shows what the issues are. Quantum computers rely on these quantum properties of matter in order to make them achievable. The problem with those with that is that you have to have a very stable environment in order to be able to see that. And building hardware that's stable enough is a difficult thing to do. And the consequence of that is that in order to achieve that, people have gone to very, very low temperatures indeed. Now, just like with classical computing, with classical computing, you can build a computer as it were out of anything. You can build it. We all build our computers today out of silicon, but actually you can build it out of Lego bricks as well, because all you need to do is create the gates and so forth, and away you go. It's just not very practical on a large scale to build a computer out of Lego. But similarly, for quantum computing, you can build the quantum computer out of any quantum entity that you like. And actually, after all, we are all made out of quantum entities. So people have been looking at a range of different technologies to build quantum computers. And we're at a point now where we don't know which one's going to win. So superconducting, IBM, Google, Microsoft are all pursuing this superconducting technologies. But it's not clear that will be the winning technology. The reason that they're all pursuing that is because it's relatively easy to fabricate. You're building stuff out of silicon, in fact, and everybody knows how to do that. All these companies know how to do that. But they require extremely cold temperatures to get the noise down to a relatively acceptable level. And by extremely cold, what I mean is within a few millikelvins of 0 Kelvin. And so that's really a very challenging thing to do. And by the way, you also have to protect it from vibration and so forth, because otherwise the quantum noise just kills the system. So the other sort of area that's very interesting in research is trapped ions. And trapped ions are harder to fabricate, but once they have been fabricated, they are less susceptible to noise. So they do have to be kept very cool as well, but 4 or 5 kelvins, which is much easier to achieve than the superconducting schemes. The group that was here was involved in a trapped ion research, collaborative research program that is also encompassing, I think, Oxford University and a number of others. It's a European project, so it's collaborating with universities around Europe. So we're in this kind of, which technology is going to win, like the whole kind of Betamax thing back in the 70s, 80s, whenever it was. for quantum computing. D-Wave are the company that are producing a machine that you can buy if you have a spare $15 million or whatever. The machine which they build is not a general purpose quantum computer. So they have 2,000 or so. They're just talking about going to a larger size system, up to something like 5,000 qubits, but they're not general purpose qubits. They're not the kind of general purpose universal quantum computing that I've been talking about. And the consequence of that not general purposeness is that there are a number of things that you can't do. So some things you can, but other things you can't with a D-Wave. So what our strategy is outlined here. Basically, we took the view that what we need to do is to create an environment that will allow wider access to quantum computing. So to take the quantum computing out of the physics lab, if you like, and to allow people who are non-quantum computing specialists but might be interested in the kind of speed up that quantum computers can give them, to provide an environment for them. And so the QLM, the Quantum Learning Machine, is a simulation environment. And I'll show you how it works as we go through this afternoon. So it's an environment that you can run on a classical computer, and in fact the QLM itself is an appliance. It's a machine, some hardware, but just a classical machine. But on that machine, it has the principles of quantum mechanics and quantum computing embodied in the software stack. And then that provides a programming environment for people to learn how to do the quantum computing. But it also provides a targeted learning environment so that you can actually look at how your quantum application might behave on real hardware. And I'll show you how that works as well. But we also do our own research into quantum computing or quantum algorithms. We're particularly interested in cryptography and machine learning. And we are not ignoring the hardware. So at the moment, it's all, if you like, a software environment or a simulation environment. But we are also collaborating with people who are building hardware, so that when the hardware becomes mature enough, we can essentially swap out the QLM hardware, and swap in a QPU. That's the intent. So the simulation approach. The value of the hardware is that you get quantum speed up, and that's obviously what everybody would like to get. The downside is it's very challenging to actually build. You need it's still very much in the lab. You may have seen these pictures that IBM produced 6 or 9 months ago of their machine, which they will sell you. But first of all, it's very expensive. It needs to get to very close to absolute zero. But secondly, it's not clear how well it really works, because the technology is not sufficiently stable at this point. So it's quite hard to use, or I'd even say very hard to use. And one of the benefits, I think, of the simulation approach is that you can test what hardware is doing against theoretical, what is correct theoretically. And so we have actually sold QLM systems to quantum hardware developers as well as for teaching and so forth. So the value of a simulation approach is that although you don't get the quantum speed up, what you do get is the speed up of the algorithm development, and that's the place at which we are now. Or that's, you know, if you're not actually in the business of developing quantum hardware yourself, but you would like to take some benefit from it when it does become available. You know, how do you go and use it? Well, the answer, I think, is to you know, have an environment where you can develop. So that's, I think, what we're trying to produce with the QLM. The QLM, maybe I've said some of this already, in which case I'll just move along anyway. It is a hardware system, so that's the system there. It's just a computer, if you like, but it has this software stack system on top of it, which provides the quantum environment. This is a representation of the different elements of the QLM programming environment. Is there a pointer?
I don't think so.
I'll talk about it anyway. So on the left, this is or the top left here. This ACASM thing. So this is the Atos Quantum Assembly Language. Okay, so this is the set of gates that are a universal set of quantum gates. And so this is, if you like, the basis of how to build a quantum application. It's a language, it's a language definition, but it's an assembly language. And you know, that's, if you like, the level that it's at. But we would probably rather not go back to the time of programming computers with assembly language. I did that once upon a time, a long time ago, with classical computers. It's fairly painful, not to be recommended. So on top of that, we built a Python extension, so you can program the QLM using Python, and I'll show you how that works as we move through. Then there's a compiler, and the compiler compiles the ACASM or the PyACASM to a binary format, which is this circ thing here, and it's the circ entity, binary entity, which is given to a simulator, which then produces the results. So that, if you like, is the heart of the QLM. In addition to that, we've got some libraries to provide libraries of commonly used algorithms and an interoperability framework, because we recognize the fact that we're not developing quantum hardware or quantum software in a vacuum. There are lots of other people doing work, and so the interoperability framework allows you to, if you are thinking of or targeting particular hardware, to use those the software associated with those systems more easily, interchangeably with the QLM. And then on the right-hand side, there are some optimizers. So these optimizers are let me talk about them one by one. The circuit optimizer is similar in concept to an optimizer for a classical computer. It's just rearranging the gates in your circuit to make it more efficient, intending to be more efficient. But there are particular challenges associated with quantum hardware that also need to be addressed, which are helped by the pattern-based optimizer and the NNizer, which is not a great name, but there it is. It's the pattern-based optimizer allows you to aggregate gates or to dissociate gates to target systems that you may have. So what we have with the ACAS language is a set of 13 different assembly language entities, but they may not be represented by all hardware, or they may not be available on all hardware. So if they're not available on all hardware, then you can create some rules in the PBO which allow you to substitute some of those gates for other ones. And the topology optimizer is intended for situations where the quantum hardware that you're using doesn't have full connectivity between every qubit and every other qubit, because that also may or may not be what happens in real life. The other piece of the environment is this green thing, the physics piece down here. The physics, so the QLM gives you the opportunity to see what noise would look like on your algorithm. So I've talked a little bit about noise already, but it is really, really important. And so one of the things that you might like, one of the questions that you might have is, developed a quantum algorithm, it works, speeds things up, that's fantastic. But what will happen when it hits the real world? What will happen when I actually want to run it on real hardware? Well, you can actually simulate that by using the physics module. So you will know from the characteristics of the hardware that you're using, the coherence time and the rate at which those qubits and so forth decohere, and so that you have the parameters that you can put into the physics module. And so for example, IBM publish the characteristics of the IBM-Q system as it stands today, and we can put that into the physics module, and so you can see whether or not it actually will, your algorithm will actually work in that environment. The QLM is sold as a modular thing, so it starts. So each one of these is a conventional 2U high, so it's, pizza box that's that sort of size. So that's a QLM 30, and then it goes up and up in size, up to 41 qubits. Because of the nature of qubits, everything depending on everything else, you have to do it all in memory. So the important aspect of the QLM, or the important aspect of one of these calculations, is how much memory you have available to you. And that's why you see, the QLM 30 is a 1.5 terabyte machine, stretching up to the QLM 41, which is a 48 terabyte machine. But you can actually upgrade machines as you go, as problems become bigger. But one of the things that you notice is that the QLM 40, 24 terabytes, is only 1 qubit away from a QLM 41. So that kind of gives you more of an indication of the power of exponentials, if you like. It's twice the size of the machine. This is half a rack in size, so it's that high off the ground, if you like. This is a full rack in size, and it's only 1 qubit bigger. So that's kind of giving you a view of of the scaling of quantum problems. Now, in fact, these numbers, QLM 30, 35, 38, and so on, are a little bit of marketing, really, because, in fact, well, I'll show you some more later on. You can expect that some problems. It depends on the complexity of the problem as to whether or not you will be able to fit, I don't know, a 32 or a 35 qubit problem onto a QLM 30. You probably will, in lots of situations, be able to do that. But if you then apply noise to the problem, then that's a very challenging thing to do computationally, and that will drive down the size of the problem that you can fit onto any particular machine. Okay. So, what the QLM does then is it allows you to develop a circuit, to simulate it, and to see what the results look like. And you can see, right the way across all of the probability distribution of the result, and that you get with a single run of the QLM, or the single run of your application on the QLM. What we also do is we provide a range of different simulators here, which are listed here, the linear algebra, Feynman, and so forth, because they have different strengths and weaknesses, and so different ones can be better applied to the different problems. What I'm showing here is what you can use the QLM for, what uses it has. So you can learn how to do quantum program development, but you can also do testing, to think of, or to do debugging. You can create hybrid code. It is just a classical computer, so you can run it, with a hybrid in a hybrid environment, and do optimization. I've shown you the optimizers. So the development process would be to write something in either PyCasm or ACasm, compile it into this cert format, and then execute down here, so that you to get the results. And it's that's the point at which the simulators and so forth can run. And the hybrid approach is fairly obvious and I suppose straightforward. So what we expect to happen is that if you develop code on the QLM, in the future it'll be possible to substitute in actual real QPUs. And we're working with a couple of different European projects to make sure that the QLM environment that we are developing is compatible, so that that will be a straightforward thing to do in the future. So we're making a bet, I guess, against what will end up being successful. So this is going down into more of the nitty-gritty to show how some of these pieces work. And I'm going to go past some of this fairly quickly, because it might be more interesting, I think, to before I go past it too far. So this is an example of an application. So you're defining a couple of qubits, defining some classical bits, running a Hadamard gate on qubit 0, and the C0 gate, and so forth. So you can see that the mapping between that and the circuit that's generated here on the right. And the Python is just, as I say, a Python extension. So this is the Python, and this is the point at which I should switch over to the MyQLM. That's the emulator environment that's on my laptop. So if you get a QLM, the QLM environment is, as I've described it, but it comes with MyQLM, which is a sort of cut down QLM environment that you can run on your laptop. And it's open source, so the MyQLM can be distributed to anybody really who is trying to learn how to do quantum computing. So students or interested people who are looking to figure out how this stuff works. And as I have it here, it's kind of perhaps more interesting to look at that rather than to look at the PowerPoint. What the MyQLM has is, or perhaps doesn't have, is it doesn't have all the features of the QLM. And particularly what it doesn't have is the noise module. And it also doesn't have some of the optimizers. It's also got only a single simulator to run against, so just the linear algebra simulator. I'm thinking that maybe I should just skip ahead, or maybe even just move out of that and show you the. This is a Jupyter notebook, and maybe, I don't know if you're familiar with Jupyter notebooks, probably, yeah. So Jupyter, the thing about Jupyter notebooks is they're great in the sense that you can get to a machine from your web browser and run Python on it. And so this is just running on my laptop here, and then I can go to look at a notebook that has a bit of a QLM in it. So defining a program and defining some qubits and applying some gates to the qubits, and then going through the compilation process, and then finally looking at what I did. Okay, so this isn't actually simulated in this particular example, but it actually shows you what it is you just in a graphical way, what it is that you've just written, and then so with this one, so this is creating an entangled pair, similar kind of idea. Creating a program, defining some qubits, applying some gates, and actually it's a very simple thing and a very straightforward thing to entangle a pair of qubits, and then there it is. And then executing it, and writing out the state. And in this piece I've run it, and then printed out the results. So this is the state with the amplitudes here, and you can see that they are identical there because of the entanglement. And then you can actually look at what that might look like in the assembler. So you don't have to write an assembler, but you can then do that. And this one is doing quantum teleportation. Stepping through, looking at it. So that's the quantum bit, and then measuring the results here. And running it and getting the results here. So the values are the same, but the signs have changed. I don't know where that is. So that is the QLM software. If I flip back now to PowerPoint, and these show, well, this did go back into full screen mode. So this shows the kind of transformation that the NNizer will do. So this is a user constraint. Then the thought is that in this particular hardware, you only have this kind of relationship between qubits. So qubit 0 can talk to qubit 1, qubit 1 can talk to 0 and 2, but not some of these other ones further down the line. So what this NNizer does is it rearranges this whatever application that you originally wrote into something which can be run on that particular hardware environment. And this, as I say, is quite sort of common today in the state of quantum computers. You can't communicate from every qubit to every other qubit. And this is this actually shows the topology arrangement of the IBM Q. So it's rearranged. And the pattern-based optimizer gets rid of, in a way that's defined by you or by a particular environment. So some of these types of operations are identity operations, so they can be removed, and that will take them out. So it analyzes the circuit that you have and reduces it down to something which conforms to that rule set, whatever the rule set might be. And in this example, if you don't actually have a CNOT gate in the hardware, you can actually change that to this sequence of gates, a Hadamard, a CZ, and a following Hadamard, to emulate the effect of a CNOT gate. And this is a little a graphic which shows the PBO operating on a much more complex circuit. The different simulators are shown here. Just a few words about them. They have different qualities. Some of them work better on different or they are more efficient, if you like. And so what you see here is the runtime of a particular algorithm, the quantum Fourier transform. As you go up in terms of numbers of qubits, with the Feynman on the left-hand bar and the linear algebra on the right-hand bar, you can see that the Feynman algorithm is much faster, much more effective at running a QFT, and so you can actually go to a much higher number of qubits on that particular size of system, because the linear algebra kind of will just take a very, very long time indeed. So the linear algebra solver, or the linear algebra simulator, is much more general purpose. The Feynman simulator is not so general purpose, but for what it can do, it's very efficient. And this shows a QFT on different flavors of machines. So here the blue bar, or the deep blue bar, is running on QLM 30. Actually, you can go to a bigger machine than the QLM 30, obviously up to 32 there. It takes quite a lot longer, but it can be done because we're using that more efficient simulator. So the features, I won't go into that because I think I've already spoken about them. And I think I've probably spoken about most of this. So I won't go into that any further. But just a few words about what happens in the real world. And quantum noise is really the piece here that I wanted to cover. So quantum noise is, well, it shows a list of noise from different sources here. And the graphic I'll come to in a moment, show you why that's there. So what this is trying to illustrate is a quantum application. So you've got 3 qubits, you're doing some step, and that transforms the state of the qubits, another step, and then you finally got some output. Now, in the normal course of events, you don't really know what's happening in your quantum application. So it's like it's happening inside a box which you can't see into. But when noise happens, noise affects those bits, or can affect those bits, and if you could see into the box, you'd see that the noise can actually transform the state of one of those qubits, which then the application carries on, but you have a transformed or a changed, a modified output. You have a bad result. So, in order to simulate that, or in order to figure out how that might be, with a QLM, you create a circuit, and then from your understanding of the environment, from the gate specifications and from the environment, then you create a noisy circuit. And that's one of the things which the physics module of the QLM gives you. It transforms the application that you've written in this kind of way. So you start with this kind of pure, if you like, pure. So this is a circuit that would be running on a pure environment, but then you put in the gate times and so forth associated with the environment, and then you have a modified set of gates. So this is not a Hadamard, this is a noisy Hadamard, and this is not a C0, it's a noisy C0. And by the way, the qubits themselves, they decohere over time as well. So instead of just being lines, if you like, they're lines that time out, or that have a possibility of timing out over time. So that while the application is running on that Hadamard, or while the the hardware is running that Hadamard gate, some of these other qubits in the environment might decohere or might change their state. So that's what the noise module does in the QLM. And so that's what this is showing. In fact, so this is the result of a QFT. In fact, so this is the QFT of a SAW function. So it's just got a couple of entries here as the frequencies. Okay, but this is unfortunately something which I can't show you on my laptop. But when you run it in an environment which has the noise characteristics of the IDMQ, you see that there are subsidiary spikes caused by the presence of the noise. So that's the ideal, and then in the orange you have the result of the noisy quantum simulation. And of course, in that particular situation, you may be able to say, well, actually the signal is really understandable there, and that's just a feature of the noise. But what you'd like to know perhaps is if your algorithm actually survives the real world. So I think that's pretty much what I had, and you've been very silent. So if you've got any questions, I'd be very happy to take them. Or if not, then there's still some pudding over there. And so, go ahead.
I'd like to ask about a possible teaching demonstration, so you could say how sort of easy or whatever it wouldn't be to work. If you had, say, 3 students trying to do a quantum encryption problem and someone trying to crack it, I mean, is that something that you could easily simulate using this in real time in a class? So you have with 3 separate students?
I think it would depend on who the students were. It's not something which I would be confident of doing right now in front of you. That's certainly for sure. Certainly, I mean, in order to get to a point of building a quantum cryptography algorithm, you would probably want to be fairly familiar with how to do quantum programming. And so that would take several steps to get to that point. But at that from there on, why not? Absolutely. There are other.
Right. So I've got some limited understanding of the program. I understand that you got a kind of circuit,
Yep.
which is similar to a normal CPU circuit. So you can retrieve the probabilities at the end and then you get your answer.
Yeah.
But let's imagine that you got a problem with millions of entries, I don't know, a list of people, and you want to find someone. How do you pass this data into your circuit?
You would have a hard. So the QLM or any quantum computer would not be able to. It depends on how you map the data on the problem onto the quantum algorithm, I suppose. So it depends on how many qubits that problem would translate into. So if you think of typically you might need more than 1 qubit for every one of those, 1 or more than 1 qubit for every one of those entries. So assuming it's 1, which is obviously the simplest case, then you'd have a hard time because we don't have quantum computing systems with interqubits. So you would be at a point of evaluating whatever analytic algorithm that you had on up to 41 entries. So we are at this stage where you can't really use a quantum computer You can evaluate algorithms.
If I can be more precise,
Yeah.
If I've got a machine learning algorithm, I've got millions of images,
Yeah.
and I want to find the best network.
Right.
I will understand that maybe the gradient descent can be done very quickly, but how do I pass all my images to that quantum computer? I will need 1 bit per pixel of each image. That's what was saying.
Well, I mean, as I say, I don't know exactly how you would do that. People are looking hard at how to do quantum machine learning right now, and I'm not really very familiar with that work. But I would certainly encourage you to look at the quantum algorithm zoo and see what has been done in that area. It strikes me that probably doing image analytics using a quantum computer is a bit of a way away.
No, yeah, because I would imagine, I don't know, factorizing a number. I can imagine that the number can be embedded in some circuit.
Yeah.
Or any other kind of.
But you know,
yes, the question is about I/O. How do you do heavy I/O with a quantum computer?
well, I mean,
Yeah, more or less.
Do you need to compile the data into the initial program?
I'm sorry.
Do you need to compile the data into the initial program?
Yeah, I mean, right now you do. Well, you have to set up the state of the quantum computer, right? So you have to build that into how you build the circuit.
You mentioned simulation and physical modules. What sort of problems can be solved currently in those modules? And would they be open source so that you could draw comparisons between that and the conventional code?
Are you talking about the noise module?
Well, you mentioned, I took it to mean simulation of physical modules. You had some sort of means of solving standard unstable Laplace's equation, for example.
Right.
Have you got a module there that solves that could be used as a demonstration, drawn side by side with conventional programming and the like?
Well, as I say, we are at baby steps right now, and so the kinds of things which you can see in, I'm not sure if Laplace's equation is there in the quantum algorithm zoo, but the kinds of things which I am confident are there is different solutions to the Schrödinger equation, so that you can identify the electronic structure of molecules, and you can do that very efficiently. That is like the Hamiltonian equation, for example, is easily solvable at a very efficient rate. So you take you only need a single qubit for a single orbital in the molecule.
Is there not a list of what's in there? Or something?
Well, as I say, there is a list. It's the quantum algorithm zoo. That's basically what I would point you to.
Related question. You presented some results on linear algebra.
Yeah.
Do you have any statistics on related comparison with classical computing? How they measure, how they compare in terms of computation performance? If I take a particular problem on the standard computer, then say 32 bits.
Yeah.
What is the relative performance?
So the linear algebra simulator is not just doing linear algebra; it's doing quantum mechanics, right? The only point of comparison there is some benchmarking that we have done, comparing the QLM and its linear algebra to other simulated environments, or some other quantum computing simulated environments, where we did quite well, in fact. But I'm not sure it's a terribly interesting problem. I mean, because as soon as the quantum computing hardware matures, then we won't really care what the performance of the QLM is. We are continuing to try to make the QLM more efficient, because we still see that the QLM has longevity of probably 5-10 years maybe. So we're kind of evaluating whether we can, just using classical optimization methods on the simulators, make it go faster. So we are evaluating, for example, whether or not it makes sense to use GPUs in the QLM, because up to now we've not been able to make any improvement in that area. But we continue to do that. So we will continue to develop. But it's really, it's not something which we see as a sort of end result for the QLM, because the linear algebra that it's doing is just quantum mechanics. There's nothing special about it.
You mentioned earlier that D-Wave used quantum annealing to make their quantum computers. You said their computer only has limited functionality, and can be only used in certain areas. But isn't that the whole point of quantum computers, that they're only used in one specific area?
That's true, but the limitations on the D-Wave are much greater than the limitations on a more general purpose quantum computer. So a D-Wave, if it works, can solve the travelling salesman problem. And that's great, actually, because lots of problems can be refactored into a travelling salesman problem. So that's kind of why that's their kind of their business model. But it can't do all sorts of other things, like some of the examples that I showed there. So yeah, you're right. Of course, you can't do everything with a quantum computer, but the restrictions on the D-Wave are much narrower than a more general purpose system.
What is the relationship between the QLM and specific realizations of quantum hardware?
What we've tried to do is to give the QLM sufficient flexibility that it can be adapted to simulate whatever hardware you may be interested in.
What kind of work would be needed to make an adaptation to one of these hardware?
You need to know, first of all, what the hardware is capable of in terms of what its functionality is. So what kind of gates does it have?
Yeah.
That's thing number one.
Right.
You need to know what the topology looks like in the hardware. And you need to know what the noise characteristics of the hardware are.
What are the noise characteristics? They're fairly generic, quasi-logical, technology-invariant ideas.
No. Sorry. The formulation of the noise is exactly as you say, but the specifics are vary from hardware to hardware.
Obviously, but the formats.
Yeah. They are. That's exactly correct. So you can, there's a set of Krauss operators. If you know, which so it's a well-developed bit of theory. If you know the Krauss operators for your hardware, you're good to go.
Right. So it is technology independent to a very high level.
Yes. That's right. That's exactly the point, in fact.
Yeah. But I just wondered whether it was, or whether or not naturally you were very much focused on your own developments of Atos.
No, we are focused on our own developments. That's certainly true. But what we're trying to do is to make this into a general purpose tool.
Right.
We're trying to recognise the fact that we do not know what's going to win
Yeah.
assuming some technology is going to end up as being head and shoulders beyond everything else. And so we are trying to create something which will give people who use it the possibility of changing direction should that become necessary.
Right. And of course it will advance significantly the awareness and interest in quantum computing, because it's something non-trivial to work with and play with.
That's absolutely
topic. What are they doing at Hartree?
At Hartree, they have got a QLM. It's a QLM 38, and it will be marketed with QLM as a service. So it will be available to as it were, anybody who can get access to the Hartree environment. They have got a list of projects which are which they're aiming to put onto that machine, and they have started work with a commercial customer who is very interested in the quantum computing, whole quantum computing business, and has given them a big chunk of work to get going with. So it's a large UK-based engineering company that produce aeroplane engines.
Gosh, I can't imagine.
You can't imagine it.
There are so many.
We can't imagine what it is.
Yeah.
Sorry, guys, I'm behind.
Yeah, well,
Thank you for my hand.
Can you go first?
No. So you said real. There was a slide that said real quantum speeder. Is that
Not with the QLM.
not okay? Right.
Yeah. That's one of the benefits of having real quantum hardware.
Right. Okay.
Yeah.
Okay. So, is there anything particular about hardware other than lots of memory?
Memory.
Lots of memory.
That's
Lots of interconnected memory, obviously.
Yeah.
And really optimized simulation software.
Absolutely. I mean, those are the two bits we're holding.
Yeah. What are the current challenges that they are facing in developing the hardware?
In hardware, it is not. I mean, Atos people hate me saying this, but it's not special hardware. It's just hardware. You can run it on
We
anything.
haven't heard that.
You haven't heard it?
No.
Yeah.
And just not been recorded.
Yeah. Okay. Good. Phew.
Crispin, I wanted to ask you, you seem to have backends for architectures on your quantum learning machine. Do you have backends for quantum computers that exist on the market now? So can I develop on your quantum learning machine and then run on an IBM, for instance?
Yes.
So that I can do today.
That you can do today. Yeah. And the reason is that the information that you need is publicly available. So you couldn't do it. You could not do the same thing. I don't think you can do the same thing with the Google machine, for example, because not all the details of that machine are freely available. But for the IBM, it is.
By Google machine, you are not referring to the D-Wave here. You are referring to the Google quantum computer.
Yeah.
Okay.
Yeah.
And the other question that I have is, do you have a program of access to the quantum learning machine?
Well,
I don't know, let me think, educational institutions, for instance.
You know who you think they could be.
I don't know, just making it up.
well, you can get access to the machine at the Hartley Centre because, as I say, we will be, we are in partnership with the Hartley Centre, and they are going to be allowing access through this QLM as a service offering.
How large did you say there?
38. Yeah.
The hardware is this QLM. Is it the standard computing hardware or are there any particular components that are specific to this machine?
It's standard hardware.
further question for Crispin?
I'm curious,
Garrett.
where in Atos is this being developed?
It's developed by a team that are based at our research lab just outside Paris.
Is that in collaboration with the academic institution in France?
Yes, there are a wide range of collaborators, in fact. We have collaborators at, I'm thinking it's the Sorbonne. There's a professor at the Sorbonne, I think, who is, I think that's where she is, who is a collaborator. But we also have collaborators who are developing hardware. There's a university in the Netherlands that are developing hardware that we're working with. I'm sorry?
Is that Delft?
I don't think it's Delft. I'm struggling to remember which university it is. I can't. Yeah. It's the Action program. AQTION. The quantum thing has to have a Q in it, obviously.
Yeah.
But so Action is it's a European program, and so we're part of that, and that university is in that group as well.
Thanks. It would seem, given some of the previous questions, it would seem like an obvious step for Atos to have a QLC, Quantum Learning Cloud.
Well, that's what the QLM as a service is, or that's what we hope it to be.
Through other third parties.
Well, through yeah, I mean through.
Imagine that
through Microsoft.
the price could be a barrier of entry if you want to have a proper cloud.
Yeah, I mean, the price for quantum computing, if you want to buy quantum computing hardware, is a huge barrier to entry, right?
Yeah.
But the price of the QLM machine is a much, much less significant barrier to entry. These are not expensive systems by comparison to a Z-Wave.
Is there a catalog for quantum learning machine, or is by negotiation with LoRa?
We can give you a price, but there's not a list price. I mean, what there is, as I say, it is an appliance, and so the appliance has everything in it, and you know we have prepared a proposal, or you know, like not one where you necessarily expect you to buy. For other university institutions, which we could do that the same again. I guess it would be straightforward to do the same. And it would really depend on where you wanted to, what kind of thing you wanted to, where you wanted to start, what sort of system. Yeah. Or give more options. We could give options as well. I guess it wouldn't be difficult to do with it.
There are a couple of UK universities or within the UK and sort of looking at that at the moment, and what we are doing is part funding. So there are various arrangements you can come to.
Yeah.
Seems to do so.
The utility of them is fairly limited if you don't happen to also own a quantum computer or have algorithms that you're developing that will eventually run on a quantum computer.
But that's the goal. I mean, you know, that's the intention. So it's a teaching thing, I suppose.
I guess that you want to reach. I guess that you want to do something in quantum cryptography before classical cryptography is broken.
Yeah.
Something like that.
Oh, no question. Yeah, yeah. But I mean, you know, there already are people doing that, right? And we know who they are. They know who you are, or something like that. Yeah.
Can I ask a fairly mundane question? The Python interface that you have.
Yeah.
I was trying to read the code as if it was in that, and it seems really bizarre to me that interface exists. I couldn't see anything that wasn't just writing the data. The data structure is the sending.
Yeah.
So what's the point of that? Other than saying that we can do it in Python.
Well, it's easier to interface to other code.
Easier than data.
Than data.
It's just data.
Yeah. Well,
circuit.
yeah, you're right.
Okay. But I guess people are familiar,
Yeah.
have some element of that.
Yeah.
Okay.
Yeah.
I just thought there might be some sort of temporal element to it, or there's nothing.
Any other questions from the audience for Crispin? So Crispin and Laura will be still around for a good half an hour, I believe. If anybody wants to have a chat with them about quantum learning machine or about traditional HPC, I guess that's also fine.
Yeah.
Okay, let us thank Crispin for the very nice talk.